So the plan for today is to look at Penrose diagrams. We need them, a useful tool, and it's a bit technical to learn it, but once you know it, then once I black hole of this kind, you just sketch something quickly and it summarizes lots of. Yeah. So before we do that, like lots of formal theory, let's put in numbers. Numbers, it's my turn. Numbers. Last week I was at a conference and they invited me to give a public lecture on black holes, and I thought, why don't I do things that everybody's asking instead of waiting that they ask? And this one was one of the questions. What does it feel like? So the question for you is, have you thought about that? Have you thought about jumping in, how it would feel?
A little bit.
A little bit.
Yeah.
No. And let me make it more concrete and less gruesome. When would I faint? Do I faint after entering the black hole or before? Because if I faint before, then I'm gonna be I have way less motivation to jump in. No? Do you know how to put a number on that? Do you know? Do you have an expectation?
Would you have to do like the length scale of like the spaghettification becomes the length scale of the human body?
Yeah, that's what we have to estimate. And so we first have to make it like a concrete and understand like, am I gonna be torn apart or something like, or am I gonna just faint? And when is it I'm gonna faint? That's the thing that I want to address. Can I enter? Can I not enter? And also, if I enter, what's the best way to faint later? Is there a way? Is there a strategy that you can use? And I think that before addressing those questions, there's a point to make that is, it's not that easy to fall into a black hole. You can aim, but you're gonna miss. No, don't get fooled by the calculation we all did of radial geodesics and radial. Nothing is ever exactly radial. So how precise do you have to be to fall into a black hole? So the first reassuring thing, or the first problematic thing, if you really want to fall in, is you're not going to succeed. You're not going to succeed. I want to convince you of this. Then if you succeed, then it hurts. But you're not going to succeed. Let me give you the argument for why you're not going to succeed. I don't know in what direction it is. I should have checked, but the center of the galaxy is in some direction. So if you go in that direction for 26,000 light years, you get to the center of the galaxy. There's a black hole. It's a supermassive black hole, 1 million solar masses, and things don't fall in. Things orbit around. Even things that are very close to it orbit around. You can try to hit it. It's just that the cross-section, the area, is so small that even if you have a small impact parameter, you're not going to fall in. You're going to orbit around and slingshot back. Okay? Even for missions in the solar system, it's easier to visit the outer planets. It's easier to visit Mars. It's easier to visit things than to make a mission that goes do measurements of the sun. Even the sun is small enough, it's difficult to get close. There's a smaller amount of phase space nearby. You really have to aim.
This is related to the fact that we saw that the short shell radius of a solar mass black hole is like just 3 kilometers.
Yeah, exactly. So and on top of that, when we are saying fall, it means that we don't have an engine and we don't have things that we can steer. And so you just follow a geodesic. And a geodesic is either you fine-tune it to fall in, or you're going to just miss and come back. Okay? Maybe I should ask, this was from a public lecture. Have you ever thought about this? To go around the sun. So if the black hole is that way, we're going that way at 200 kilometers per second. There's a dark matter flux under 200 kilometers per second this way. To do a round is 2 million years, 200 million years. And I always need to compare to a scale, otherwise I cannot remember 200 million years. So the big extinction where T-Rex was lost and all the other dinosaurs lost in 60. We are here 60, but sharks, they have been around for way longer. So at some point there were sharks on the other side of the galaxy. I had to say it. There were sharks on the other side of the galaxy. Okay, so how do we do the estimate of so it's clear it's an estimate of curvature when you faint. Yeah, because I'm saying I'm falling. So acceleration, there's no acceleration. Yeah, there's an acceleration. And if I was in a spaceship, I would still accelerate. And we're saying we succeeded. We're just falling. There's no acceleration. So the only effect is tidal forces, spaghettification, I'm saying. So let me do another check. Do you know how big is the curvature here? I want a number. And let me just set it. Curvature is 1 over length squared. So as a length, do you have it fresh? What's this length?
10 to the power of 11
units.
meters.
I'm gonna forget that number. I have to think way too long to get that number. Like I know acceleration is 1 light year because I know what is 1 light year. There's a way of thinking quickly about what is the curvature here. Don't think of it as length, think of it as time. Because if you say this huge thing that is like 10 astronomical units or 1 astronomical unit, why would it affect things at the scale of a meter? But at the scale of a meter, I can wait and see if there's a curvature effect. So that is the important, useful quantity. How long in time is the curvature here? And the answer is, if I tell you, you're gonna know what it means, it's 90 minutes. What is 90 minutes, 90? 1 hour and a half. You know this number, 1 hour and a half. You're familiar, have you encountered this number? No? 1 hour and a half. The International Space Station takes 90 minutes to do 1 orbit. Why? It's exactly that combination, square root of gm over r cubed with a 2 pi in front of it. And so if you were to build like not a pendulum that oscillates because of acceleration, but something rigid and hinged in the middle, this wouldn't oscillate. But in Newtonian language, the mass at the bottom and the mass at the top with a stick in between, the mass at the bottom is attracted more than the one at the top. So this would oscillate this way. Or if you want the tidal forces, I'm going to make it oscillate, and the period is 90 minutes. Same reason as, okay, so 90 minutes here, it's safe. That's why I needed this number, completely safe. So when is it that we're going to faint if we fall into a black hole? And then say that I'm speaking about this black hole, this one here. So the 10 to the 6 solar masses, 1 million solar masses. The question is, do I faint before entering or after entering? That's what I want to know. So, yes.
What do you mean specifically by faint?
Faint, I mean, let's say when vision goes down before I faint, vision goes down because there's not enough oxygen carried by blood that goes to the retina. And so first the vision goes down, and then there's not enough oxygen that goes to the brain, and that's probably too late. But I would say after my vision goes down and I freak and my ear starts. Okay, that's what I mean.
Okay.
No, and I want to fall in and also enjoy it. So I want to know when this is gonna happen.
Oh.
Okay.
That happens because of the acceleration, right?
Well, that's what I'm saying. It's not the acceleration because you are in free fall. You're following a geodesic.
Oh, right.
So it has to be a tidal, because it will be a geodesic deviation or tidal force. And so that's why I was saying, let's say that the black hole is that way, and it's big. It's so we're saying 1 million solar masses means also 1 million kilometers. So it's that way. It's big. So I have to decide: do I go feet first, head first, or flat? I'm arguing. I want to argue that flat is best. the reason that I should give is the heart is has to pump. It's easy to pump. If there's no acceleration, then you know, it's something that is known. For instance, people like the seat in supersonic jets is put so that, or in shuttles is put so that you're sitting this way, you accelerate this way, so that the heart can pump. If you are horizontal, then you're not going to get enough blood. The pressure will be too high to pump blood to the end. Okay, so same reason. So now the question is, how big should it be? This how far can I get? And so we have to estimate curvature, or if you want, we have to estimate a differential acceleration. And so, what is it that I'm speaking about? Speaking about geodesic radiation. Side of dot mu r mu r mu beta velocity alpha velocity beta direct to the u. Okay, so this is my delta acceleration. This we know is gm over r cubed. And this is the separation. So let's say the separation between, I really need from my heart, my eyes. Let's say 1 meter. Okay. And what I'm asking is this differential acceleration to be not too big. Let's say 10 G. It's a safe thing, no? And so let me see if I can do it. I want R larger, let's say order G M H over delta A power 1/3. Check that I did it right. Length 1 over length power 1/3. This is good. And see if I can do it. So this one, it's the core. So 10 to the 6 kilometers. So 10 to the 9 meters, H 1 meter. And this one, delta A, I want it to be 10 G. So this will be 10 times 10 to the minus 16, because it's like here. Power 1/3. See if I can do this. Oh, this is 8, 10 into 10 to the 8 meters. There was a meters that I lost. I have to check because I'm not sure I will find it right. Looks good. 10 to the 8 meters. Yes.
Quick question, how did you get 10 to the 9 again?
I'm assuming 10 to the 6 solar masses. And this is kilometers. Okay, so that's inside here to everything SI units. So this 10 to the 9 is 10 to the 6, 10 to the 3.
What about the G?
Oh, I never use G. GM.
Oh, GM is 3 kilometers. Yeah.
It's 3 kilometers, so this is 10 to the 9.
I see.
No?
Yeah.
That is important.
Yeah.
Never use constants. Those you use when you're doing numerics. Yeah. So 10 to the 8 meters. This is 10 to the 9 meters. I faint when I'm inside. I can even stay up for 1 minute once I enter. I'm okay, I'm gonna explore, I'm gonna check, and then it's gonna be bad. And for a solar mass black hole, you're not gonna go inside. You're not gonna. It's gonna be bad here. Yes.
How do I deal with the velocities? Like the velocity, did we just make that one?
Tell me again, these ones.
Yeah.
Yeah, I put the hat to remember that they are normalized. So that means it's really only the direction. Yeah, and there's something important in that is there is no absolute notion of velocity, because I have to say velocity with respect to what frame. And this is not velocity with respect to a frame. This is just the velocity in the sense of tangent vector to a world line. Okay? The only place where it's assumed something about this velocity, it's a velocity such that it has no acceleration. Because this is the geodesic deviation equation that assumes that it's geodesic, that is, I'm falling. Everything is parallel. My heart and my eyes are parallel initially, and they are held loosely together. So they are just going by themselves. And then the only thing that is going to move them around is just curvature. So if I wanted to be more precise, I would have had to add another piece here, like a spring that is my neck. And why did I put the spring for the neck? Because I'm tracking just blood carried by oxygen. And so that can move freely without having to put a restoring. So that's why I was saying, when am I gonna faint, or when my vision is gonna go down, and not when my neck is gonna break, because that, yeah, would have to add an extra piece. It is the force. Okay, concrete enough. You can also ask, when is it that molecules are gonna be pulled apart? When is it that electrons are gonna be stripped from protons? And you have numbers for that. No, to extract an electron from an hydrogen atom, you need 13.6 electron volts. That's the scale that you need to put inside here. And proton, can you break the proton into pieces? What would it happen to the proton? No, electron, you see, you take it out. But proton, is gravity going to break up the proton too?
But the strong nuclear force is much stronger in the short length scales, right?
Yeah, but this story about going inside the black hole and going to the singularity,
right,
is this one is going to win over every possible thing. So at some point, it's going to win over the strong force.
Yeah.
But can it win over the strong force? Do you have a guess of what's going to happen?
At some point, we'd be like plasma. Right.
Yeah, so the proton is made of quarks, but you cannot free the quarks. You can pull the more you pull them away, the stronger the force. But at some point, you're just going to produce quark and quark pairs. So you try to pull out a quark and you extract a pion, and you get a proton and a pion. And then you keep trying, you just produce more and more pions. So you're breaking it up, but in a way, you're putting in energy by breaking it up. And so you're just producing more stuff. Yes.
What is each again in the space?
Meter
Oh,
from Earth, from Earth to
Oh,
Mars.
that's
That's what I put as 1, yeah.
Oh, okay.
Yes.
And then for 10 Gs, you use the length scale associated with gravity is 10 to the minus
Yeah.
16.
So this 10G is an overestimate. I'm saying okay. So but these are things I'm measured. So I can stand 1G because we live in 1G. If you go that way, for a few seconds you can stand 10G. For a millisecond, you can easily stand way more than that. If you have your accelerometer and you check, you do this. By doing this, this is 1000 G. You can check. It's 1000 G this. Yeah. Okay, so this is this direction. If instead you accelerate me that way, for a second, a person generally can stand 3 or 4 G. And these things are like, there are tables for, want to make sure that the amusement parks are safe or don't just faint. And so you have to check that the accelerations are scary, but I just you don't faint. Okay, more questions about that. So the estimate is down here. I had for this talk, I had a list of questions, all of this kind, like what is the color of a black hole? We're gonna do the color, or do black holes have spots? So maybe we can find the time sometime to go over that. But that was all the estimate I wanted to do for today, right? And next week, the estimates, I'm gonna mark them so that you can sign up, but they're gonna be either variants of this or power emitted in black hole mergers, two black holes. So there's a few numbers to become familiar with, like what's the power of the sun? How much energy does the sun radiate? So that you can ask this black hole merger, how many suns is it? People sometimes say like brighter than all of the stars in the galaxy. But the black holes don't count, and otherwise it cannot be brighter than. Okay, so there you want a number there. Okay, are there other comments on estimate? You're familiar with the logic by now, right? Okay, so I think now we can shift gears. I really want to use the lecture to tell you about Penrose diagrams. This is really useful. You find them everywhere in discussions of horizons and black hole formation. And I'm gonna give you somewhat detailed construction of the Penrose diagram for Minkowski and the Penrose diagram for Schwarzschild. You find them in books, in the literature, but I should say before we do it, giving you the details so that you see them once. But what you have to pick of them is not the long derivation. What you have to pick is that these diagrams are summaries, as diagrams always are. There's some complicated physics. You are interested in only one property, causal relations. And so you make a diagram that tells you only what can affect what. Okay? And everything else is not part of the diagram. It would be too complicated to read the diagram that contains everything. Okay? And so in these two parts, I'm going to show you how two simple ones are built. But then in practice, how do you do it? That's going to be the start. And there are lots of places where these things are explained. I would look up Dave Tom's lectures for this one. So part one is what we already discussed last time. Vaidia spacetime. What is this Vaidia spacetime? If here you put a constant, this is just Schwarzschild that exists forever and will keep existing forever. No time dependence. But here I didn't put the mass, I put this function of V. V is the advanced time that we have to learn how to speak about completely. And I'm setting it so that it's 0 at the beginning, so that this piece is not there, and this is just Minkowski. And then it's a constant after. So it's a black hole that forms in the sense that there's no black hole before, and there's a black hole after. And I don't know if I convinced you of this last time. It's not that this black hole appears instantaneously. This black hole is built in a causal way, in the sense that there's matter that forms the black hole by falling. And if you're given this metric, you can build this diagram that is here on the left. This is RV. So what I dropped is the angular directions. You can think of this diagram as a ray tracing diagram. It's a diagram that tells you only how light rays propagate. For instance, I can send in a light ray, and it's going to go into the black hole and reach the singularity. Or I can send out a light ray, and it's going to go to infinity. And it's clear that it's useful to know light rays because all matter is in between light rays. It's in light cones. And so if you are able to build first this diagram by solving the geodesic equations for light from a metric, Then you can take the diagram and summarize everything that is in, I should use a better word, not diagram. This one on the left, I should not call it a diagram. This comes from a calculation. This I should call it a plot. No, you solve an equation with this initial condition, and you find this numerical solution. Now, the problem is so easy that I can do it qualitatively, but there's lots of details. I'm saying it's going horizontal, it's going slope 2, and then it's bending in this logarithmic way. And then there's this thing I was telling you last time that is, here it's flat. Here there's this shell of matter that forms the singularity, and it's below 2 GM, there's a black hole. But if you send in a light ray, at some point the light ray is going to be trapped and unable to escape. And so if you think of the horizon of a black hole that exists forever, it's at 2 GM, Schwarzschild radius. But if a black hole forms, this horizon doesn't appear from nothing. It forms here, it grows, and attaches here. And so it means that you can be inside the black hole even before the black hole has formed. That was the story we were discussing last time. To build this one, I had to solve these differential equations for geodesics. Once I've done it, what's the Penrose diagram? The Penrose diagram is everything that is time-like, it's a vertical line. Everything that is space-like is an horizontal line. Everything that is light-like, if it's going out, it goes to the right 45 degrees. If it's going in, it goes to the left 45 degrees. And so this singularity, I was telling you it's space-like because it's what you end up in at some time. So it's a constant time surface, it's space-like. And so it's drawn here like this. This horizon, you can show that it's null. How do you show that it's null? Suppose that you're here and you want to shoot light out. If you're here, you shoot light out this way. If you're here, if you're a bit inside, you shoot light out here. And if you're just at the horizon, light is going to stay at the horizon. It's this portion here, 45 degrees. Okay? So the first thing is that it straightens things so that everything is either horizontal or vertical 45 degrees. The second thing that it does is here you have to send R to infinity to cover everything. And this takes infinity and it moves it to a finite place. It's compactified so that it stays in a piece of paper. Okay? And so everything that is here, I can describe it here in this diagram by saying it was for space. I threw in some matter. It formed a black hole. The black hole is this. This is the interior of the black hole. And this one, I should also consider it as the interior of the black hole in the sense that once you get here, you're trapped. And this is the outside. Here, there's no curvature. It's flat space because there's no matter yet. And here, there's curvature as outside the star. Yes?
Why is S2 not on a
S2, yes. Yes, it's a good question because you see here, this piece touches this one and they join. While here, this one doesn't look like it's joining this one. So why did they join them? The statement is there are two things that I should not say at once. There is one thing that is, as I'm compactifying things, distances should not be read as distances in here. If I have 2 points, I don't know if they are close or far because this diagram is only causal relations. It's a summary. This point, this is all of spatial infinity. This point is all of the spatial past. And so even though here it looks like a point, I'm taking all of infinite space at minus infinity and turning it into a point. And so there's something that is unfaithful in the diagram. That is, if you cut it a little bit before, you see that this is extended, but then extending it here, it comes into something that looks like a point, but this point has infinite extent. And so this addresses the fact that also this one looks like a point, but it's all of the future. It's all of the future of let me address it more precisely. If you send light out, it's gonna go here. If you send massive things that don't fall into the black hole, they're all gonna end up here. And things that go into the black hole, they're gonna end up here. I still haven't addressed why I'm drawing this line, touching this line, touching this line. I have to admit that is an extrapolation in a regime where I shouldn't trust the extrapolation, because I shouldn't trust anything that is too close to this dashed line. The singularity is where quantum effects are important. And so I should cut a bit before, but if I cut a bit before, that means that I don't know what to do here. Okay? And so even though the diagram is completely standard and derived from general relativity, I'm telling you that it's a good practice to just cut it a little bit before and put a box here where one says, we don't know the physics here. Okay? And that is separate from the statement. This point is infinite space, infinite past. Yes.
Could you draw again the lines on Penrose's diagram that are objects that don't fall into the black hole?
Yes. So I'm massive and I exist for some time. So I will go from here to here, but you can take my protons and follow them into the past and into the future if they don't fall into a black hole. And this would be the word line of massive things like protons.
Okay, so they all those curved lines in S1, the red curved lines, they all start from the lower left corner and at
Yes.
the upper right corner.
Yes.
Okay, all.
Yeah, things come from here and then here, or come from here and then somewhere here. And that's the separation between massive objects that either fall into the black hole or not. Yes.
But I think if you're asking about the red lines, those are the, right?
Yeah, so these ones are null, so these ones go this way.
Oh.
Yeah, okay, let me say it more precisely. I was describing massive quantities. They go from here to here,
Yeah.
or from here to inside. Then you can ask about things that are massless, like light. And so I send in light, it passes through the center, and it goes to infinity. Through the center, and it goes to infinity. I could also send it into the black hole. And so there's light that escapes to infinity, and light that doesn't escape and goes into the black hole. There's also this funny thing that is, there's light here that escapes, and slightly after light that cannot escape. Okay? And these are these red curves that I am. Okay?
So that edge there where the light rays were escaping, that edge what is that?
This one?
The
No.
straight one.
This one?
The
No.
one on the right, upper right.
It's like infinity.
Tell me, is it this line?
Yeah.
Yeah, so think of a detector put very far away, and you send it farther than any possible thing, and this is a detector for light. You have to think of it as this portion here.
So
This is
then,
called future null infinity.
and then you said that point on the right was spatial infinity.
And this is spatial infinity. Yes. I'm gonna go through all of these things now. And to answer all those questions, the best way is, let's do Minkowski. Do Minkowski slowly, step by step. But I should say it again. We're gonna do it step by step to convince you that one can fill in the steps. But when you need it, you're not gonna do the steps. You're gonna do this plot. You look at it. You don't do any more calculation. You just think and draw. You think, like, if I send here, it goes here. And so this has to be a line that goes this way. This one goes inside and goes there. So that means that this one is like I should draw it this way. You really have to think of these diagrams as a summary of a long calculation and not as a conformal transformation satisfies a list. I'm really distinguishing the mathematical definition from the actual use that you think of. It's useful when you use it as a sum. So now I'm not going to follow my advice, and I'm going to derive it step by step as in books for Minkowski, because at least one has to see it. Okay? And In fact, I'm gonna do first Minkowski. Then, I don't know, you might have seen this one, even tattooed on the arms of somebody. You know what I'm speaking about. And then we're gonna do this one that is the one that I was showing you before, no, the one that is a black hole that floats. And in books, you often find this one described, the extended Schwarzschild, with all the detailed calculation. What I'm telling you that's really useful is this one and not this one. Don't get confused by this weird thing. Okay? Okay, let's do the first one, easy one. Minkowski, let's do all the steps. You have the notes, I'm gonna go fast. I only have to tell you what is the logic. I don't have to do the calculations. You take Minkowski, it's invariant under rotations. Extract the spherical part. That we understand, it's just spheres. How do I know that this is radius? Because here there's r squared times unit sphere. That's the definition of radius. Radius is the thing that spheres have area for pi r squared. And so all of Minkowski for us is really just this piece, RT. You can also go to double null coordinates, UV. How do you do that? Well, you say U is T minus R and V is T plus R. So that these are coordinates adapted to light, going inside and going outside. Okay, C is 1, clearly. And so you just do this change of coordinates and you get minus du dv. Check that, make sure that you're familiar with that. That's a way of writing Minkowski. I'm not done yet. I still have to do another thing. I need to, this u and this v go to from minus infinity to plus infinity, but I want to pack everything into a finite region. So how do I do that? I do a conformal transformation. Conformal transformation means that I take the metric and I write it as an overall factor times what is left. This overall factor omega squared is the conformal factor. It's allowed to depend on coordinates. Why it's useful to extract this overall factor? Because light never sees that. Because if you set this to 0 and this factor is non-zero, you can just drop it. It means just this piece has to be 0. Okay? Let me follow the logic step by step. I'm only interested in causal relations. Causal relations are given by light. If something can be connected via light cones, then it's causally related. But light cones never depend on this factor. So let's just extract this factor in a way that what is left as coordinates that run between -1 and 1 or minus pi alpha and pi alpha. Okay? That's the logic. And so what you find in books is you first do this step, which is actually useful, adapted to light, and then you do the second step that is useless. It's just like you are overdoing. You are showing how to take an infinite line and turn it into a segment. It's not useful for calculation, but it's useful for the drawing, because now the drawing is, this is Minkowski, T and R. I first changed coordinates, V and U. And then I compactified the coordinates so that V goes from something to something, and U goes from something to something. And so now I can address some of the questions that we had before about what is this point, what is this point, what is this point, what are these lines. So here are all the names. So if you have, let me do first the grid. These are constant Cartesian time. This is one, this is another, this is another, this is another, this is another. No? And then I can do constant radius. This is radius 0, radius something, twice times something, 3 times something, up to infinity. And so what is this point? This is spatial infinity. Fix a time and go to R infinity. You're going to go to this point, spatial infinity. And then you can also say, well, fix a radius and send time to infinity. You're always going to go up here. Independently of where you start, you're always going to go up here. And so this one, I plus, is time infinity, temporal infinity. Future, this is past. And this is drawn as a point. But this is the place where all massive things are going to end. they're gonna end because we compactify them in a finite region. Yes.
So confused by its triangles, which are.
Yes. Inequalities. Radius cannot be negative.
Oh.
Okay? That's all. Because otherwise, if it could be negative, then I would draw it as a rectangle. No? So this is R equals 0. Sometimes people put also the other part. Sometimes they don't. To avoid confusion, sometimes I put like something like a mirror here, so that you are right there and you go out. Why I'm saying this? Because when people draw this one, they are putting something on the other side, and we really have to answer, what is this thing on the other side? Is it negative radius, or is it something else completely different? Okay? Good. And there was something else to say. That is, in Minkowski, you can send light, and light goes out of the window and doesn't come back. Where does it tend? Well, it tends here. All of the light that goes out at this place is called future null infinity. And if you send light in, all light is coming this way. So it comes, goes through the center, and goes out. Okay? And the diagram is adapted to light. And so light gets a large portion, and space or time gets small portions. This is not faithful map. This is a conformal map. It only shows you what is next to what in a causal sense, but not how big countries are. Yes.
So the future null infinity and the I plus I0 and I minus are actually all the same size, but one is just an edge.
Yeah. This is infinite. This is infinite future time-like. This is infinite far away space-like, and they are points. And this is infinite for light, and this is extended because you want to make sure that then you can tell what can affect what. And so you're zooming out things for light and down things for space. Okay, that is all there is to know for Minkowski. Maybe there's one more thing that I can say. That is, suppose that you accelerate. Suppose that you're following this line. This is inertial, Cartesian. And then at some point you start accelerating. You arrive here, you start accelerating. You accelerate, that means that you deviate from that one. But have you ever thought about that? If you accelerate at 1g, which is safe, you don't faint. So you could build a spaceship that goes at 1g. Direction, center of the galaxy. Center of the galaxy is 26,000 light years away. If you go at 1g, how long is it going to take to get to this black hole at the center of the galaxy? Do you have it quick? I want it quick. So you go at 1g. So first it's safe. You just have this small engine that just makes you in your spaceship as if you were at home. You point in the right direction, and you keep going always at that acceleration. How long does it take to get to the center of the galaxy? A minute, 1 year, 1 century, what did I say, 26,000, a few 100,000 years. Okay, let's do it. Minute, century, 100,000 years. I want to say it's 100, it's, what did you say? 20,000 light years is going to take 20,000 years. Or no, it's going to take much less. It's going to take 1 year. Why is that? You haven't thought about that. You haven't thought about that. Okay, let's do it. Now, this is important. This is the same question as how long does it take light from the sun to the earth? So suppose, how long does it take to a muon to come from the, when I say how long, you have to say along what word line, not what frame of reference, not with respect to whose perspective, which clock, you have to say which clock. So if I say a muon, the muon carries a clock. How long the muon's clock measures from when it leaves the sun to when it reaches the earth? Short, not 8 minutes. Certainly shorter than its lifetime. I'm asking the same question. How long does it take to me, with my own biological clock, to go to the center of the galaxy if I go at 1G? Not 1 second. The question is it 1 year? Is it 100 years? Is it a few 100,000 years? 1G. Let's start from rest.
What's the distance again?
26,000 light years.
1,000.
What is G as an acceleration? What is it?
Yeah.
How long is G? Acceleration G, 9.8 meters per second square, as a length, as a time.
A light.
Right.
No.
90 minutes.
So it's 1 light year, so as a
Oh.
time it's 1 year.
Yeah.
How long does it take to get to the center of the galaxy?
6,000.
It's gonna take 1 year, maybe 2 years.
Yeah.
No? Yeah. Let me draw it. It should become clear once I draw it. I start here at rest. I go at constant acceleration. Didn't draw it right. Start here at rest. I go at constant acceleration. All the question is, how long does it take from going from rest to sufficiently close to the speed of light? Because from here on, it's 0 time. And from here to here, the only scale is G. That is 1 year. You do the calculation, get there's a factor. Right? It's gonna take 2 years. So you haven't read Project El Mary. That's the reason. Okay, the movie is coming out. You haven't read Project El Mary, is that right? No, it's a cool book and it's crucial for the story. So maybe I spoiled part of the story. If you go at 1G, you get everywhere in the universe if you want in 1 year, in a couple of years. Yeah. The book also, somebody's very confused by this. What's the problem with going at 1G? Yeah, the problem is that there's CMB here. At some point, you have a large impact with CMB. There are cosmic rays coming. You're just going to get all of this wind, high energy, and that's going to be the problem. It's dangerous because of that. I shouldn't say anything anymore because otherwise I spoiled the book, I spoiled the movie. But do this calculation before you go check the movie. No? 1 year. G is 1 light year. That means 1 year is the time scale. Okay? And so the thing that I wanted to tell you is
What's the book in the movie? Project Film Made by
Yes. It's open spelling it right. The book is good. Movie, I don't know, but the book is good. The reason why I'm saying it is that you see, even if you go at 1G, you are eventually gonna go null. That means that if you go at 1G, if I go from me, I start going at 1G, eventually I end up here. Even if I'm massive, if I was able to go constantly at 1G, I will. So why I'm saying this, you probably know about the Rindler wedge. In Minkowski, RT, it's this curve of constant acceleration. If you take the curve of constant acceleration, it's this curve here. Okay, and we did Minkowski, just Minkowski. Now we want to do Schwarzschild. We have to do the same thing for Schwarzschild. And don't forget the lesson of you derive this metric outside the black hole, when R is larger than 2gm. And then you should trust it only there. But you can do this extrapolation of, well, it looks like it makes sense also if it's smaller than 2gm. I just don't know what happens across because you get a 0 here and an infinity here. And we are going to do something of that same kind, even more drastic than that. No? We're going to do an extension. It is, extension is a way of saying we're going to do something wrong. We're going to extend coordinates in a place where it's not a diffeomorphism. However, the thing we're going to get in the end, if you take it and you plug it into Einstein equations, it's a solution. And so that was the thing that one should have done from the beginning. Yes.
So was the Minkowski one was not in the context of the black hole being there?
Yeah, so this Minkowski one is just Minkowski, no black hole. No, it's really special relativity.
Okay, thanks.
Yeah, and somehow when one learns special relativity, one never discusses acceleration, but certainly one can accelerate in Minkowski. Okay, so let's see. This part you recognize. This part you recognize. This is the areal radius. So the first thing that we want to do is to take this piece and write it in double null coordinates, U and V. U for light that goes out, and V for light that goes in. And then what you're going to pay is that there's a conformal factor. Now, be careful. I'm calling this conformal factor, but it's just for this part. Well, what people call a conformal factor is one that is for all of the metric, something like this. So there's going to be a second step. But this first step is already interesting. So let's do this first step. How do I write things in this way? I need to find coordinates that are double null. So I'm taking this part of the metric, imposing that it's 0. That's this equation. And then we solve it in the simple way of doing dt in dr. And there are two solutions. Light going out, light going in. And this is not integrated yet. You just put an integral in the area, an integral in the area, and that defines U and V. Sometimes instead of being called that way, you integrate it, you give a name to this dt integrated, you call it R star, as Regen Wheeler do. And you call it tortoise coordinate because instead of being like R that is fast, it's a slow tortoise. And then if you want, you can even invert it. And the inverse of this log R plus log, it's a function that has a name. People give names to functions when they use them too much. And you just give it a name. Lambert W function. And if you put everything together, and I know I'm going fast, but you really don't need the steps. I'm only showing you that one can fill in the steps. Once you've done all that, you find that Schwarzschild can be written as the UdV with a factor in front of it. These are called Eddington-Finkelstein coordinates. I'm not done yet because I still have to take this factor and put it in front of everything, and I have to compactify everything. And so this is something that was done in the 60s, discovered in the 60s. It's Kruskal and Zekeresh. Well, how do you send something that is infinite into something that is finite? You put a log or you put an exponential. And so this is one more change of coordinates. Now, I didn't say it correct because this one sends something goes from minus infinity to plus infinity to something that is one negative and one positive. So if you just do the change of coordinates, you get this quantity. Let me just show you. So this is outside the black hole. This is inside the black hole. In these double null coordinates, this is the outside of the black hole. This is the inside of the black hole. These coordinates by construction, this is negative and this is positive. But once you're here, you can say, well, why not taking it all the real line and not half of the real line? Why not, instead of taking this 1 and 2 region, I don't extend it also to negative U and negative V. And so now you get 4 regions. Here there was region 1 and region 2, outside and inside of the black hole. And now there's outside of the black hole, there's another outside of the black hole. If you live on this outside of the black hole, you can never visit the other outside because they are causally disconnected because, because light rays go this way. This is not compact yet. We still have to do another thing that compactifies it in a finite region. You do this last step. Arctan is always the trick. And when you do that, you end up with, see if I have it, too many things. I really put all the details if you want to see them, but yeah, it is. This is the summary. So let me show you. So this is RT, familiar Schwarzschild coordinates. This is somebody at constant radius outside. This is somebody falling in. And there's always this puzzle of, do you have across the horizon? Well, in RT coordinates, they are bad at the horizon, so it's a bad question. Now we have coordinates that are good across the horizon. So the same line goes from minus infinity to plus infinity. If I drop something, it crosses the horizon and falls into the black hole. But now we have done this weird extension where we have allowed this other part, where you can have somebody outside the black hole that also drops something in and falls into the same black hole. But this infinity here and this infinity here, they are really different infinities. Now, this is this thing that sometimes in popularization they describe it as there's this piece of paper, you can go to infinity, there's another piece of paper, and then in between there's this thing that you can fall in, and you end up into the black hole. From the other side, you can fall in, you end up into the black hole, but in popularization, they allow you to do this thing that you tunnel from one to the other. You cannot do it. The causal structure is you come from here, you go in, you come from here, you go in, but you cannot go from one to the other. Okay? Is there physics in this picture? No. This is a black hole that has existences forever. You see, it has even as a singularity in the past. So this part at the bottom should be called a white hole. No, things that come from here would come from a singularity. We cannot predict what's coming out here. More importantly, a black hole that forms should still be a solution of Einstein equations. Is it this solution? No, because this exists since forever. Even more, this has also another universe on the other side. So what is a black hole that forms? This is the last part, and I think it's the important one. It's also the justification why it's important to know this. One is formal, because it's a solution. It's good to know all the exact solutions. But physically, this is one page. This is the last page. And it's the one page for which I needed all the things that we did before. We learned Minkowski. We learned extended Schwarzschild. Now, suppose that you take a piece of Minkowski and you say, here I cut. I say, here there's a shell of light that falls. And I cut at this shell. And here it's Schwarzschild, all of this is Schwarzschild, but I also here I cut at this shell that is a null shell. And then I say, I don't trust any of this part, and I don't trust any of this part, and I take this and I glue it to this one. What do you get? You get our model of ideal spacetime. And now you know by construction that it's a solution of Einstein equations here. It's a solution of Einstein equations here. The only place where it's tricky to know if it's a solution is where you glue. But you go check, and then there's an energy momentum tensor that is exactly the one of a null shell going in. And so you have this new technique now of building new spacetimes, new solutions of Einstein equations by taking known solutions, cutting them, and gluing them. Okay? And this is the same that before I was telling you, like, look, we wrote a solution, We did ray tracing, we mapped everything, and the summary was this one. And now I'm telling you, like, I didn't really, if I had already done this work before, I could have just cut and glued and said, well, this is a solution. Let's ask what's the physical interpretation. Okay, we have 15 minutes for discussing because this is all I wanted to cover. 1 and 2.
So we can kind of go along any null shell or. Are there
You-
restrictions?
Cutting along null shells is easier because the system is made for null things. But I could even cut, and this is an important thing, I could say, suppose that I have, not even suppose, let's consider a neutron star. What's the geometry of a neutron star? And what's the Penrose diagram of a neutron star? Well, the outside of the neutron star is Schwarzschild. The inside is approximately constant energy density. So I would take a space-time that is approximately constant energy density, also called Freeman-Robertson Walker. I cut a ball and I glue it to Schwarzschild. I could do also something more dramatic. I could say, suppose that instead of having a neutron star, I have something is empty inside. It's just a shell. A shell with nothing inside. There's nothing inside. Inside is Minkowski. But outside the shell, there's Schwarzschild. Now, the fact is that this shell is stationary, but not null, it's time-like. So in Minkowski, you cut something like this. Time-like. You keep the interior flat, and you glue it to something here that is the exterior. This is called Oppenheimer-Schneider. And so you can say, like, now you could even take this shell and say, well, initially it was in equilibrium because it was supported by its own pressure. At some point, it stops burning whatever can give that pressure and it collapses. And then you have one more thing. You can do something like the analog of this one, where instead of having this cut here, you have the cut that goes like this. And it's flat inside, massive shell, and Schwarzschild outside. Okay? And then I can even say, like, suppose that now, after a while, I send a second shell of matter, and I make my black hole grow. Well, it would be like sending a second shell, and then a third shell. And so now you can really treat dynamical situations by building over simple building blocks. You have to keep track. 1, 2, and 3.
Can I just add that because.
Yes, please.
The consistency conditions, I think, are that the intrinsic metric from either side, the intrinsic metric or the sub-interval has to match. Yes. And also you have to fill in whatever stress tensor is appropriate to solve the other parts of the Newtonian equations. So, and those are called like the Israeli junction conditions.
Thank you. Yeah, that's important. You cut and you glue, you impose the area from one side and from the other, they match, or the intrinsic geometry from one side and the other match, but then you cannot match everything. Otherwise, if you match everything, you're matching initial conditions, so it means that they're matching the solution. So the only thing that you are not matching is this extrinsic part that you encode into energy momentum.
So you can cut and glue anything subject to those conditions.
And you can build new solutions. And I'm really saying, let's not get fooled by the fact that we learn a few exact solutions, and then we think that those are the solutions. General relativity has 2 degrees of freedom per point. There are plenty of solutions. We set initial conditions, there are solutions. So here we are really speaking about things that we can easily write pen and paper. We have a few of them because they have symmetries, like Schwarzschild, the Freeman-Robertson Walker, like the Minkowski. But then you can still take them and say, it's this one here and this other one here, and I'm gluing them together, but I just have to be careful where I go. No? There's, for instance, a model of cosmology people consider, where one says, Freeman-Robertson Walker is exact homogeneity and isotropy. But suppose that you have bubbles with higher density inside a region of lower density, or high density with bubble or lower density. Well, lower density, you know how to do it. High density, you know how to do it. You cut and you glue, and they call this a Swiss cheese cosmology. And it's a good model of inhomogeneities in some cases, or larger models.
How would the interest change with this version?
It becomes less useful because you are assuming spherical symmetry to draw it, and there you don't have spherical symmetry. And so it is still useful for saying there was some, people still draw these things. They say, well, there's something that happened here. For instance, they even draw it as a binary here, and there's gravitational waves that come out. And so you say how much energy is emitted from here to here, like 5% of the initial masses. And then you say there's a final black hole that forms. But to speak up really about the merger, where you have two black holes, all of those notions of horizons and of dynamics, they all make sense. But the nice simple diagram where you have only R and T is not capturing it, everything. So if you have neutron star merger, it's good enough. But black hole merger, it's showing only the part of the final black hole and not the ones of the black holes that make it. Okay? And so in that sense, one really has to take it as a tool, as a diagram that sometimes it's useful, but not necessarily always. And if one knows the derivation, then one knows the pitfalls. Okay? People who think about Hawking radiation and about black hole evaporation, they describe scenarios of what happens to a black hole when it evaporates completely by just giving a diagram. Is there something that survives, a remnant? Is there a large universe trapped inside? Does the black hole disappear? And so you see diagrams of this kind. Diagrams on this kind. And at some point, if we have time, we discuss these things, some quantum effects. The plan for next week is to first do horizons. And I think it's clear that this one is the Schwarzschild horizon, R equal to GM. This part here is a bit surprising, that you are trapped even before matter fell. So next time, what I want to do is to make clear what are the ingredients that define these dynamical horizons, horizons that change in time. It's time for another comment. Yes.
Since there's the region 3 and 4 in the Pascal diagram, they are like extensions of where you can actually where extensions where your definitions don't really make sense because the log goes to negative.
Yeah.
Then why do we even draw them in the first place? Right?
It's a fair question. Like there's a fact. The fact is, take this metric with U and V that go negative.
Yeah.
This R is defined here intrinsically.
Mm-hmm.
Okay? You take this one, you plug it into Einstein equations, and
Yes.
this is a solution.
Okay.
So this is a solution, it's a good fine solution everywhere.
Right.
The real question is, does it happen out there? Is it ever realized? How would you prepare this? What initial conditions? And so you could say, well, certainly I cannot put the initial condition down here because there's a singularity, but maybe I can put it here, the initial condition, or somewhere here.
Yeah.
I have two universes with some thing in between such that they evolve into a single black hole with two sides. You need two universes, and then you can try to. And so the more straightforward and less speculative way is, look, I have this universe, I have matter, this matter force and force is black hole. This is the solution outside, but inside I shouldn't trust it because inside it's matter. It's not Schwarzschild, but inside there's matter, so it's more like homogeneous geometry. The curvature doesn't increase. The curvature here is 93 minutes. If you go inside the Earth, it's not gonna diverge at the center of it. No, just there's less mass.
Right.
Okay. Yes.
Thing. If I put initial conditions on a Cauchy surface in my universe,
Yes.
it predicts what happens inside the black hole too, right?
Yes.
So does it mean that if I have to put initial conditions in the other universe, in a Cauchy surface of the other universe, that has to be consistent with the initial conditions of my universe because they have to be consistent in the black hole region?
Yeah, so this would be Cauchy.
Okay.
Yeah, you cannot do Cauchy that is like, I don't know, something
Yeah.
and then something. You really have to do something like this to make Cauchy.
I see.
In this point, this is a bifurcation surface in technical sense. Good, let's stop here. Thank you.